So what I wanted to do, first of all, we go over the problem, and I would show you a little bit about how differential data flow works. And the reason it occurred to me that regarding the videotaping, depending how we feel after, we could like show it to other people, although I doubt they'll want to watch it. So I probably won't bother with that. But I want to try and teach it to a few people to get the idea of how to teach it anyway. So first of all, did you understand this problem I had, or this idea I had of let's compute the subset relations but without reference to location?
Subset relation. Let me think. Let me think. I'm trying to translate the stuff. Maybe like if you can explain a bit more, like or give
Yeah.
more con
How do you open Vim actually?
Vim, type Vim.
Just type Vim? Okay. I never know. Uh, I'm so inclined to type VI, and I think VI is like a different thing, right? It's like the same
Yeah.
binary, but it behaves differently. Let me show you. Okay. So here's the naive analysis. And there's this subset relation here.
Yeah.
And in particular, it includes the point P. And so what I was saying is we can compute a subset relation, let's call it I don't know what to call it. I'll call it subset anywhere, which says basically at any
It gives
point,
you a list or something of points and
well, it just says, does this hold at any point in the program?
okay, yeah.
Ah,
Yeah, it's much better for me if you like when you're talking about this stuff, like do what you're doing now because kind of like on the fly, like
yeah.
it's hard for me to translate the stuff. But yeah, I know what it was this about. So yeah.
Did I ever tell you when I was in Switzerland, I was taking French lessons, but in a German-speaking place. And they would ask me to translate from French to German. And it was like, no, this is not happening. Like French to English or German to English. But anyway, I understand. So I guess what we can do, but actually what I want to do here is not modify this file. I just realized. So I have that naive, that's supposed to be the like, just as it is in the blog post,
Yeah.
known to be correct because obviously correct. So let's make a new file. We'll call it location-insensitive. There's a word for this. What's the word? Oh, I guess that's fine. And we'll have to add a module for it then. All right, so now we can kind of modify this subset. So let me explain what's happening here first before we start changing it.
Yeah.
So this is the differential data flow code, right? And I've kind of commented what the datalog rules and what the corresponding code is. But it probably looks to you like gibberish. At least it did to me when I first started looking at it. But the idea is each of these variables kind of represents some set of tuples. So here we have a variable that's like all the outlives tuples. And we're saying we'll clone that set and say, okay, for all the outlives tuples, that we're going to call that subset 1. Okay. And then here we're going to derive a new set of tuples, subset 2. And we'll do it by, we're following these rules, right? Which say that the transitive closure relationship. So we say if there's a region R1, and it's a subset of R2, and R2 is a subset of R3, then we want to say that R1 is a subset of R3.
Yeah.
And so if you think about it in terms of like a database or something, that's kind of how this is working. So what this says is we have to do a little grouping. So we take we start out with a 3 tuple with R1, R2, and the point. I don't know why I called it Q here actually, but it doesn't really matter. Let's call it P. And then we're just going to reorder them so that we have R2 and P together here as the first half and R1 as the second half. And the reason we do that is the first half is we're going to do a join. So we're going to take two sets of tuples and combine them based on what they have in common, right?
Okay.
And in order to do that, we have to identify which parts are we joining on and which is the other stuff that we carry along. So it's just like it's literally the same as a SQL database join, right?
Yeah.
And if you look at these rules, we want to join, we have two sets of tuples, the two subsets. And we want to join them based on what they have in common. The first one has R2 and P appearing in these positions.
Yeah.
And the second one has R2 and P appearing in the first and third position. So we map it exactly like that, right? We take R2, which is in the second position, and we put that and P together in the first half. And then here we take the same thing, subset.
Yeah, makes sense.
And we map it like in the same way. And you see that I'm kind of pretty strict about my names. Like you could use any names for these variables, but I'm always trying to use the same names that are in the bar because otherwise it becomes impossible to like keep in track what's going on. So the ordering of these things may be different, but the names should always line up. So now we have this, and we can join them. And what we get when we're done, we get a 3 tuple. This is the thing in common, R2 and P. And this comes from the first half, R1, and this comes from the second half, R3. And then we can map that, and like we don't care about R2 anymore. We only needed it to find the lining up, so we drop it out.
Exactly.
And so it's very simple, kind of.
Perfect. Yeah, makes sense.
And the rest of this is the same idea, but here a semi-join is just like a join, except it's more like a filter, right? There's no extra data that comes from the right-hand side. Mm-hmm. So we're just seeing if it's in this set, then we keep it, otherwise we drop it. And it's a little bit of a pain in the ass. You see that I have to do, because this rule has an or in it, that's what the semicolon means. Mm-hmm. And differential data flow doesn't have like a concept of or exactly. You have to kind of break it into 4 computations because there's 4 possibilities. You know, either it's like the first one of both, or the first and the second and the first. And so that's why I have these 4 things here, A, B, C, D. And then I kind of, at the end, we take all these things and we concatenate them all together.
I see, yeah.
And then we use distinct to say drop any duplicates. So the same thing might come from more than one. And that's the total set of tuples.
Perfect, yeah.
Okay.
Makes sense.
So what we want to do then is just simplify these rules to like, I was just thinking, you know what I should have done? No, we'll see. This is going pretty well. Maybe it would make sense to schedule like a larger group code walkthrough with whoever can make it, you know.
Yeah.
But anyway, what I want to do here is, or if we don't want the position, then we can simplify these rules, because now we're tracking what is the subset at every location separately. And if instead we just want to track what are the subsets that occur anywhere, I mean, that, for example, that's what the AST-based borrow checker does. It doesn't care where you came up with this relationship. It just tracks that one region has to be a subset of another region, right? And that makes it a lot less data because it's not multiplied times the size of the graph. So I think, if I remember what I wrote in that, well, okay. Do you want me to quiz you? I'm gonna.
Yeah.
Let's start like this. I think that the datalog version was something like this. We have a subset. Man, I hate Vim. What? I don't know why I can't type. Anyway, and we have a rule like this. It's a very simple rule. The idea is RA has to be a subset of RB if at any point there's an outlibs relation.
Yeah.
So here's my quiz. How on earth do I do this? And it's fine if you don't know, because but I'll give you a hint and start out like this.
So you have like what you have is like an outlives relation at point P,
Right.
B, and you want to generalize that, but
Right.
I mean, what I maybe don't not understanding from what you wrote there, from the rules, like what does P means there? Like, I mean, I know it's a point, but would be any point, or because if it's just one point, like the thing, I don't understand how that makes sense. Like
Okay.
it's any point P.
Yeah, any point P.
Okay, yeah,
Yeah.
now it makes sense. Yeah.
Sorry, it's always, there's actually an implicit, for every variable that you use, it's implicitly sort of for all. So for any point P. But if you use the same variable more than once, it has to be the same one at each spot. That's the only thing.
Exactly. Yeah, makes sense. So, well, of course we iterate over this.
Yeah. Actually, it's kind of already iterating, but yes, you're right. That's the right intuition. You can think of them as iterators. Oh, so yes, okay. So now we have the set of tuples, and we're iterating over it. And there are going to be three tuples: RA, RB, and P.
Yeah.
So how can we make a two-tuple out of it that doesn't have P?
You just drop P.
Yeah, exactly. We just map it in particular, right? So say like RA, RB, P, and we'll just map it like this. And now the only problem is we'll have the same tuple more than once.
Distinct, yeah.
So we can do distinct. Actually, distinct total is the same thing but faster. I think it only applies if you're using some fancy features. Then you have to use distinct, but we're not, so we can use distinct total. And I guess it's a faster algorithm. So
yeah, in the way you asked the question, I thought it was trickier, but
yeah, I thought you might think that. It's a trick question. It's too easy. But basically, yeah. So that's the subset relationship now. If we don't care about position, then that's all we have to do. And I think we're kind of just done. You could add the transitive closure rule, but I think we don't want to because it will be expensive. And ideally, we will find ways to not have to compute the transitive closure. It's probably not that expensive, but it's more expensive than not doing it.
Okay. Yeah.
So let's see. So we can delete all the rest of this stuff. It might be, just for fun, let's do it. Let's compute I'm going to show you how you would, if you wanted to compute the transitive closure. This is how you would do it. You would say, there's a couple of ways, but so there's this method called iterate, and what that does is, for something like subset, you have to compute it in rounds. Right? You start out with a base set, and then you add more things that you derived from the base set, and you keep doing that until you reach a fixed point, which is everything. So that's what this iterate method does. Is you call it on the base set outlives, and it gives you like a closure which says subset here is going to be the result from the previous round, and you have to compute the result of the next round.
Okay.
So we would do something like, let's call this subset base. This is just like the raw the base facts, right? And you would have to start with the facts that you always have to include the base facts, because we're computing what's the next set from this round. We're not only computing the new values, but the full set of values. So it should always include all the old values and then add more. And then we're going to say something like, so this is sort of this rule. And then we wanted something like RA, RB, if, the transitive closure rule would look something like, if you know that RA is a subset of RB, and you know that RB outlives RC at some point, then you know that RA is a subset of RC. All right, so now I am going to quiz you again. Let's see if we can write this rule. Only I'm going to do one thing before I quiz you. I'm going to write this in a way that leads us more to what we actually want, I think.
Yeah. So let me see. So you want to get subset base. So from the subset base RC, I mean you have the you have the outlives thing. You need to get the subset base first. So you need to do something like what we did, like in the previous example.
Yes. Well, we have the subset base right here, right?
Well, okay, use that.
Yeah.
Yeah.
Actually, we have to do one thing, which is just sort of you just have to do it. When you create an iteration like this, how is it? What's the name of it? Okay. If you have some variable that you made outside the iteration, you have to call enter, and now you get a version of the variable that's like inside the iteration.
Okay.
that's just like a technicality. But yeah, but otherwise we can use any set. These are like functional sets. We can just use them as many times.
Yeah. Okay. Yeah. So now we need to join
Yeah, exactly.
the stuff.
So how do we
Similarly.
which variable or how? Yeah, we need to do a join. And we need to do some maps to like identify.
Yeah, you need to change the order of R A and RB.
Right, so something like subset.map.
Like exactly, and then like shine directly with what you really have.
Yep.
In yeah.
How do you? What's the key to use one of these completions?
To what? Sorry. To
when it's
to complete
a tab or something. Oh, okay, tab.
Yeah.
Okay. Yeah. Okay, so good. So yeah, if we do this join, that's exactly right. And then
and then you map and discard the first thing,
right,
and get the.
So I think we will have RB, RA, and then RC. So we just want RA, RC. I think that's right. It looks right. And then we just have to do this thing. We have to concat. Damn it. It always feels to me like enter should do this auto completion. But it doesn't. I think that's it. That'll compute the transitive closure of the subset relations.
Can you explain a bit I mean, I'm kind of starting to look at this stuff. I don't remember very well what was the purpose of like a location-insensitive thing for this. Like, I mean, it kind of I could guess that at some point you will you will need to know all the relations between the stuff to build all the subset relations between the regions and stuff, so the compiler can do the right thing. But I mean, I'm trying to imagine where exactly are you going to use this location-insensitive
Okay.
relationships.
So here's the idea. This is basically the same analysis, but less precise, right? And in particular, it won't handle some of the examples where, let's say you borrow some, well, it doesn't matter that much, but let's just say some of the examples we want to handle, this will reject, because it doesn't take into account where a subtyping relation had to hold. It makes it hold everywhere all the time, instead of saying it only needs to hold in this part of the program. And
yeah,
the idea is however, because it's less precise, there are a lot less like tuples in terms of, very practically. There are just far fewer tuples because you're only making relations between regions and not between regions and points.
yeah.
So you have a lot less data. And so the idea was, if we do it, in fact, it's actually not that common that it matters where the subtyping relation was established. There's some examples where it matters, but a lot of examples it doesn't matter. And so the idea would be, if we first do the analysis this way, that should be faster, but it would get more errors, right? So we can take those errors, and that tells us, let's do the expensive analysis, but just on those loans and at those points where we got an error from the cheap analysis.
Okay.
And if we know like we only care about a specific loan, when we do the expensive analysis, that lets us use a subset of the total set of tuples, right? Because basically we don't have to propagate data for the loans that we don't care about. We only have to propagate data for the one loan that we're interested in, and not only for the one loan actually, but for the one point where we're interested. And that probably means we only care about a subset of the control flow graph, right? Only those points that are on a path to that point. So the idea was exactly that. So we can use this first analysis, which I think should be quite a bit faster, and filter down those parts of the function where we actually care to get a more precise result. And then if we're lucky, we never need to do the precise result at all, right? And if we're unlucky, we do it for a couple of loans and that's it.
I see.
I think that should be a big win. I mean, if you look at well, you don't have to look at it now, but I have a branch which modifies the existing borrow checker to be location imprecise. And it gets pretty big speed wins. It's like 60% faster. And, only one test fails. And another way to look at it is all Rust code that exists passes with a location imprecise check, right? So we know that most Rust code doesn't really need this full precision.
Yeah, I see.
So
yeah, that's more or less what I wanted to know. Yeah, because
So I suspect it will be just a small minority of functions where we have to do the full analysis. And then the reason I thought that now, in order for this whole scheme to work, we need to have the invalidates facts, because those are what let us figure out where the errors are, which we can then use to refocus. But we don't need them. We can start by doing like what we're doing now, sort of what we would do if we had those facts. There's still a lot of things that don't actually depend on them. We only need them to make the connection between the two phases, if that makes sense. So what I had hoped to do basically is what we already just did. There's another relation, which is the requires relation, that we could define, although I might stop at this point and work with you over Zulip or something, because I want you to type it yourself. It's always very different.
Yeah, of course.
But basically I figured we could write these up and just measure how long does it take. It won't be giving us a result. The downside is we have no way to check that the result is like what we expect right now, because we can't see what errors we get from the compiler. But the good side is this, I think just by reading your code I can probably find, like, the dataflow stuff is sufficiently high level that you don't usually have bugs, actually, or at least once you get the hang of it. It's more like the analysis is wrong. That may happen, but the code itself just works.
Yeah. And so also, like, your blog post mainly talk about like location insensitive, like most of the stuff that you describe is about this. I mean, I don't remember.
Well, I think in the blog post it was a location. I presented it, so it was a location. If you look at the formal rules in the blog post, they always have a location in them.
Yeah.
But I often talked about the rules sort of at a specific point, the way I would present it. And at one point, you can sort of ignore the locations. But it was a location-sensitive analysis, the way I presented it, nonetheless.
Yeah, exactly.
Whereas this one, if the rules just don't talk about points anywhere, right? We're just dropping all the point information.
Yeah.
Now.
Yeah, I don't know what it said, but I think it said it the wrong way. I mean, like you talk about the location sensitive,
I
not
see.
not. I don't know
Yeah, yeah,
what is.
that's right. I talked about it. This is a new idea, basically. I was
Mhm.
thinking last night that this ought to be quite a bit faster. This basically ought to let us have our cake and eat it too. Um, so,
Yeah. At the same time, like well, you said that most of the Rust code like would be enough like analyzed with this thing, but yeah, kind of like we're talking like very in the abstract, so it's kind of hard for me to imagine like why like what is the code that needs location sensitive like.
yeah. Do you want me to show you an example? I can show you an example.
And at the same time, why most of the code like doesn't need that, like I mean I can't imagine like why.
Right.
I don't know, maybe it's because I'm not that used to Rust yet, but
Well, it's no. I also have a hard time with this. It's not just you. Let me show you an example of some code that would need it. Ah.
I guess that's because most of the code doesn't have like complex relationships, let's say between lifetimes and stuff like that, or
Yeah.
or it's
So if
not.
you look at this code, this example I'll show you. This is exactly the case where you need it, and I think it just doesn't happen that much. Um, so first, you have a mutable reference, in this case to a vector. Okay,
Mhm.
and then I make mutable borrow here, p, and
Mhm.
sometimes I return it. But other times, I don't use it again, and I modify the map. Today, this won't compile. And the reason
Mhm.
is because you because here you sometimes return it, we have to assume that the borrow lasts all the way until the end of the function and then some more, because if you return it, it has to last until the end of the caller, right?
Yeah.
But that's only true if the thing is true. It's not true if it's false. Then you're not going to return p. So we're going to reject this program, but it could pass, and sort of should pass.
Yeah.
And also the analysis, this location insensitive version will reject this program. It thinks about it a little differently, but it's the same idea. It will make a subset relation here saying that, well, whatever this anonymous lifetime is, let's call it tick A or something, saying that it'll say, okay, here, like if P is if that's the type of P, then here we will
Yeah.
require that tick P has to outlive tick A or tick P less than or equal to tick A, depending on your point of view. And
Mhm.
since we're not considering the location, that will mean that this borrow, like here we know that if this is the lone L0, this is the lone L0, and we know that tick P requires L0 here.
Yeah.
And so we are going to,
Yeah. The subset relation doesn't hold like after the if.
right, but it will in the insensitive version because,
Yeah. Exactly.
yeah,
Exactly. Yeah. But shouldn't,
right,
like, yeah.
exactly.
So that's why it fails.
So what? And actually, now that I think about it, this will probably do. We may want a kind of hybrid. We'll have to see. The existing borrow checker actually is partially location sensitive. Now that I think about it, so the subset relations are not. Just like we wrote here, they don't consider the location at all. However, the equivalent of the requires relation is. So we understand that. That's why. Let me show you an example where that would matter. If you do the exact same thing, but we do hold on. But we do this. Sorry, to yank yank. If you do this function, it will borrow check successfully today. And the difference is basically that you created the loan inside the if and not outside. And we know that we do track when you make a loan all the points that could follow from the point where you made the loan. Right? So it's partially location sensitive. And we may find we actually want to do that now that I think about it. Which would mean, in terms of the tuples, it means that requires would still have a point, but subset would not.
Yeah. You mean that it's like how was the word you used, like location?
Partially location sensitive.
It's not like scope based or something like that. Like
the borrow checker, no. This part is not scope based. It just it finds the point where you made the loan, and it finds all the things reachable from that point in the control flow graph, which are still inside the lifetime of the loan. So there is a sort of interaction, I guess. It's like if the lifetime is confined to a certain scope, then it will stop at the exit from that scope because it exited the lifetime. But the other propagation is not based on the scope. So it's kind of this weird hybrid. In any case, these are the two examples where, or these are the kinds of examples where location sensitivity matters. And I think this first one comes up rarely, but it certainly happens. And today people just work around it by transforming it into the second one, basically. So sometimes that means you have to do the loan twice, essentially. Once to test if you should return, and then again when you actually return, which can be less efficient. So for a vector, it's fine. But for a hash map or something, it might mean you have to do the hash map lookup twice. That's usually where this happens. So very interesting. So now I'm thinking, well, okay. So two things. First of all, I'm thinking we should probably end this call, or we could stay, but either way. But we can write out the data log anyway, and make a version. Let's make a fully location insensitive version. So we'll basically make the rules for requires, and just measure how long it takes. That's all we care about right now. And then we can make a version where requires does track the location and see how long that takes. And that would be useful data, basically. Uh,
Yeah, yeah, yeah.
and then
Okay, can do.
go